Math 2414, arc length video 6, arc length function example. Find the arc length function for f of x equals the square root of x minus x squared plus arc sine of the square root of x on the interval 0 to 1. This problem looks much harder than it is. You would think that this is some insane sort of function to take the derivative of, and not only do the derivative of, but do all this to its derivative. But at the end, you'll see that, yeah, it was kind of designed to work. All right, recall that to build an arc length function for a given function, we set up this integral from the beginning value to x of the square root of 1 plus the square of the derivative, but everything is in terms of t in the integrand, because x is being used as the upper limit of integration. Oh, there is one small thing that I left off on the previous video's definition of the arc length function, is that the arc length function is only defined for values of x that are in the original interval of the original function. So this x can start at a, but if it did, these would match and the integral would be 0, which makes sense. If you start and stop at the same place, you've traveled a distance of 0, but it can only go as far as b because that's all we know about this function. All right, so let's get into it. First thing we have to do is take the derivative. Now, before we take the derivative, we might want to rewrite all the square roots as 1/2 powers, so let's just do that over here. And for those not in my class, you may be wondering, why am I using the arc sine notation instead of sine inverse? It's just a personal preference. All right, let's take the derivative. The derivative of the first term, power rule, bring down the 1/2, leave the inside alone. So it's still x minus x squared. Subtract 1 from the exponent to get negative 1/2. But then the chain rule says times the derivative of the inside. The derivative of x minus x squared is 1 minus 2x. So there's the derivative of the first half of the function, plus the derivative of arc sine is 1 over the square root of 1 minus the square of the sky. But then the chain rule says times the derivative of the inside. The derivative of x to the 1/2 is 1/2 x to the negative 1/2 power. And we got what seems like a huge mess. Let's clean it up a little bit before we even consider squaring it, because that's our next move. The first half of the derivative is going to need a fraction because we have a negative exponent. So let's go ahead and figure out where everything's going to go. The 2 and the 1/2 will go on the bottom. The x minus x squared to the negative 1/2 can go downstairs and become a positive 1/2. And then the 1 minus 2x, not having any reason to go in the denominator, is going to go in the numerator, specifically because it's already up there because it's over 1. Let's move this down a little bit. 1 minus 2x over 2 times x minus x squared to the 1/2 power. Plus, same thing over here. We got fractions all over the place, so let's make one big fraction and see where everything goes. This square root is already in the denominator, 1 minus, and inside the square root we have x to the 1/2 to the second. So we can multiply the exponents. 1/2 times 2 is just 1. So that cleaned up nicely. The 1/2 has a 2 in a denominator. And then the x to the negative 1/2 would put the x to the 1/2 in the denominator. There's nothing left in the numerator, so it's a 1. Okay, this is looking kind of bad, but right now my biggest concern is that we're mixing using radicals and fractional exponents, so we need to choose one and run with it. Now right now we're not doing the calculus because at some point we're going to integrate, but we're in the midst of algebra, and it might be a little more convenient from an algebra perspective to turn all the 1/2 powers back into square roots. So in the first fraction, 1 minus 2x on the top, 2 on the bottom along with the square root of x minus x squared, plus, and in the second fraction we have 1 over 2 square root of 1 minus x, and then this x to the 1/2 we can rewrite as the square root of x. But if you'll notice, we have a product of square roots here, and as long as they're not both negative, we can put them together and multiply them. So let's take this to the side real quick and see what happens to it. If we multiply the square root of 1 minus x times the square root of x, we can put them together and multiply the 1 minus x times x under 1 square root. But if we distribute that x, we get the square root of x minus x squared. Well, that's really handy. Not only is it handy because it ends up matching the square root in the denominator of the first fraction, but now we flat out have common denominators, period. So we can add the fractions together. Common denominator is 2 times the square root of x minus x squared. And the numerator is going to be 1 minus 2x plus 1. We can combine the 1's to get 2 minus 2x. Look at all them 2's on the top. If we factor out a 2 from the top, we get 2 times 1 minus x. And now both the numerator and denominator have factors of 2 which can cancel, because you can only cancel parts of multiplication problems and fractions, leaving 1 minus x over the square root of x minus x squared. So I think we have simplified the derivative as much as we possibly can. Why don't we erase everything and just move the derivative right up here? It's a nice thing about watching a video. If you didn't get something written down, you can back up and catch it again, or pause the video. Okay, so it was a little bit of an algebraic song and dance, a little bit of shucking and jiving, but we got the derivative, but we're not done setting up the arc length integral yet, the arc length function, because our next move is to take that derivative and square it. And if you're wondering, when am I going to put the t's in there? When I set up the integral. Squaring this derivative isn't nearly as bad as it might have seemed at the beginning, because all we have to do to square a fraction is square the top and square the bottom. The square and the square root cancel on the bottom, leaving x minus x squared. And if we square the numerator by writing it twice and foiling it, or using the formula for squaring a binomial, we'll get 1 minus 2x plus x squared. And if you're tempted to start canceling things, stop. You can only cancel parts of multiplication problems. Oh, wait a minute, parts of multiplication problems. I just undid a multiplication problem on the top. Maybe I should put it back. Because look at this denominator, which is not a multiplication problem unless you factor out an x. And that will leave 1 minus x. And now both sides have a common factor of 1 minus x. So we can cancel one of the 1 minus x's on the top and the 1 minus x on the bottom. If we wanted to, we could split this into 2 fractions, but I don't think that would be the intuitive move most people would make. So we'll leave the squared derivative there. This keeps getting better. Oh, now we gotta add 1. 1 plus the squared derivative is going to be 1 plus that. But this is a fraction addition problem begging for common denominators. The only denominator is x, so we need to make both fractions with an x on the bottom. 1 minus x on top of the second fraction because it's good to go. But to get a common denominator of x on the 1, we would just put x over itself. And now we can add these fractions together by combining their numerators, but look, x and negative x cancel, leaving a 1. So this nasty, messy function, after differentiating and squaring and then added 1, collapses all the way down to 1 over x. So that's the thing we're going to park underneath the square root. So our arc length function is the integral from the lower limit, which was 0, to a generic upper limit of x, the integral from 0 to x of the square root of that last result except with a t. And even this is an easy integral because the square root of 1 is 1. The square root of t is t to the 1/2, but it's in a denominator, so if we move it upstairs, we get t to the negative 1/2. This is an easy calculus 1 integral. Add 1 to the power to get t to the 1/2. Multiply by the reciprocal to get 2. This is being evaluated from 0 to x. If we substitute x, we get 2x to the 1/2. We substitute 0, we get 0, so we could have ignored that. And if we change the x to the 1/2 back to a square root, we've got our arc length function. Therefore, our arc length function, s of x, is equal to 2 times the square root of x for 0 less than or equal to x less than or equal to 1, because that was our interval over which we integrated. So what that means is, if I graph this thing, and to be honest, this is the entire domain of it, because if we put anything negative, then this is negative under the square root, bad. And if we put anything bigger than 1, this becomes negative, and more importantly, oh wait, this tells us that we can't put anything bigger than 1, because if we put something bigger than 1 and square root it, we get an answer bigger than 1, but the domain of arc sine is just between negative 1 and 1. So that's actually the function's entire domain. But what this function says is if we had that function's graph, then this function would tell us how far we travel if we go to a certain x-coordinate. And again, in calculus 3, physics, and engineering, the concept of an arc length function is kind of critical. And that's the end of this video series.